Okay, let's first start with work. Work, as we know that when force acts on a particle and produces some kind of displacement, then we say that work is said to be done. And work done by a force, work done by a force is given by that work equals to force dot displacement, that we call as dot product. Also we can write as Fs cos theta if a body is kept and a force you are applying, and due to this force the body has been displaced up to here. This is S and the angle is theta, right?
Right.
So work you can also write is F multiplied by S cos theta, or you can write here F cos theta multiplied by S. That means either you take the component of displacement in the direction of the force, or you take component of force in the direction of displacement. Then you multiply that into, then you get the work done. This formula we use when force is constant. Force is constant. Work done is a scalar product example, dot product example. So it is a scalar quantity. Its SI unit is force multiplied by displacement, that is Newton meter. Also you can call it as Joule. Okay, this is basically clear.
One second. One second. I'm just copying it. Yes, sir. Done.
Okay. If force is not constant, like here one example you can take that let's suppose force vector is given as 2i cap minus 3j cap plus 4k cap, and a body is displaced, a body is displaced from point P whose coordinate was 2, 3, 4, to point Q whose coordinate was 3, 1, 5. So if they say what is the work done here, find work done. So in that case, first we find force is given. So displacement we can find by the final position vector minus initial position vector. So final position vector is here 3, 1, 5. So I can write here 3 I cap plus j cap plus 5 k cap, and initial position vector is 2, 3, 4, that is 2 I cap plus 3 j cap plus 4 k cap. So if we subtract these two, then I think 3 minus 2. 3 minus 2 will be 1, that is I cap, plus 1 minus plus 3, this is minus 2 j cap, plus 5 minus 4 is plus 1 k cap. That is the displacement vector. Now, after finding the displacement vector, now we can find the work. That work formula we know is force vector dot displacement vector. Force vector is 2 I cap minus 3 j cap plus 4 k cap dot, this is I cap minus 2 j cap plus k cap. So this dot product we know I dot I is 1. So 2 into 1 is 2. J dot j also 1. Minus 3 and minus 2 is plus 6. And k dot k is also 1. 4 into 1 is 4. So the work done answer will be 12 joule. This is the answer for work done. You understood this example, Neil?
Yes, sir.
Please copy it.
Oh, yes, sir. Done.
Okay. Now, if force is variable, if force is variable, in that case, work done you have to find for a small displacement ds, and then you have to integrate it from whatever displacement is given, let's suppose 0 to s. That is the that means you take a small displacement and in that you use the force and then you integrate. That is the rule. Sometimes if I say in this formula, if force is given in vector form, like suppose F is given like Fx component of Fx, this is along x-axis, Fy along y-axis, and Fz along k, that is z-axis. And displacement is also happening in that way also. I can say dx is along x-axis, dy is along j-axis, and dz is along z-axis, k cap. So this formula I can write as work done equal to integration of and the body is getting displaced from one point to other point having the coordinates. Okay, so I can say that the body initial coordinate was, let's suppose, x1, y1, z1, and from there it got displaced to point q having the coordinate x2, y2, and z2. So if I write this f dot ds concept, I can say this is fx I cap plus fy j cap plus fz k cap dot. This is dx I cap plus dy j cap plus dz k cap. And the limit will be, uh, first point is x1, y1, z1, and other point is x2, y2, z. So here I dot I is 1, so you can integrate fx dx separately, and for fx dx you take the limit is x1 to x2. Then you can do j dot j1, then you can integrate fy dy, and for that you take limit from y1 to y2. And for fz dz you also integrate, and for this you take the limit from z1 to z2. So that means in all axes you have found the work done separately and then you have added. This is also a formula when the force is variable. Okay, one formula is this, and its extended version is this.
Yes, sir. Done.
Okay. Based on that, I'll take one example that also you understand. Let's suppose I have been given a force F is 2x I cap minus 3y square j cap plus 4k cap, and a body is displaced. A body is displaced from a point P, that is 1, let's suppose 2, 3, to Q, that is 2, 4, 5. Let's suppose like that. So what you should do, first you should understand what is the component of the force. You can see that this is Fx component, this is Fy component, and this is Fz component. So we use our formula, that is integration of Fx dx from x1 to x2 plus integration of Fy dy from y1 to y2 and Fz dz from z1 to z. It means that Fx means here 2x, so we have to integrate 2x, and that we have to integrate from x1 is 1, x2 is 2, from 1 to 2. Fy, we have this minus, I think here, this is minus sign, minus 3y square dy, and y limit will be from 2 to 4, from 2 to 4. Then we have z component, which is only 4, there is no variable there, and that we have to vary from 3 to 5. Constant you can take outside, x integration will be x square by 2, and the limit is 1 to 3 will be taken outside, y square integration will be y3 over 3, and that is from 2 to 4. 4 is outside, dz integration will be z simply from 3 to 5. 2 I can cancel, 3 I can cancel. So x square means here I am getting 2 square minus 1 square. Then y cube, this means 4 cube minus 2 cube. And here z only, that is 5 minus 3. This is 4 minus 1, 3. So I'll write here 3, minus sign here. This is 64, 4 cube minus 2 cube, 8. 64 minus 8 is 56. 5 minus 3 is 2. 2 into 4 is 8. So 8 plus 3, 11 minus 56. I think it will be negative 45 joule. Understood, Neil, this solution?
Yes, sir. Just 1 second.
Okay.
Yes, sir, done.
Okay. Now, as I said that work done is also equal to uh, integration of force with respect to displacement. And we know that integration is also geometrical meaning of area. So you can also say it is area under graph, area under force displacement graph. That is another method to find the area, force displacement graph. So if you have a force and displacement graph, and graph may be like this, and you want to find the area between displacement S1 and displacement S2. So you can take the space between S1 and S2, enclose it with displacement axis, and then you can find the work done. That is F dot ds, and the integration limit will be from S1 to S2. Understood? If I take one example here, and here one thing you have to very much remember, that the area above will be positive. This area will be positive, and downward if some area is coming, then this area should be negative. So if I take a force displacement graph here, let's take a force displacement graph, and it is going like this. Let's suppose this is given 2 Newton, this is 0, this is 2, this is 4, this is 6, this is 8. And let's suppose this is also minus 2. So I have to find the work done in this condition. So if I say total work done, is work done means 0 to 8 here, total work done if I have to find in this graph that I have drawn. What you see that there are two areas basically. One area is this triangle. So this triangle area will be half into base into height. Base is 0 to 4 means 4, height is 2. This I'll take the area as positive. But this area, this triangle area, I have to take negative because it is in the fourth quadrant. Force is negative here. So if I take negative, same we will find that this is half into base is 4 to 8, that is 4 only, and the height is also this 2. So again you will see this both are same only. So total work done in this condition will be 0. Okay.
Okay, just one second.
Yeah.
Yes, sir, done.
Okay. There is one more formula to find the work done, and that formula we say as work energy theorem. Work energy theorem. But to understand that, we need to know about kinetic energy. We know the basic formula of kinetic energy. It says that work done on a body, work done on a body is equal to change in its kinetic energy, equal to change in its kinetic energy. If the body is moving in a horizontal road, okay, the body is moving in, there is no change in potential energy, moving like this. Then if here the mass is given m, here also m, here velocity is u, and here velocity is v. So just to, even if you don't know what is the force acting, how much is the displacement, no problem. You can find the work done just by using the concept kinetic energy final minus kinetic energy initial. And that is half mv square minus half mu square. By that also we can find the work done. For example, or here a few more points. If final velocity is more than initial velocity, that means particle velocity is increasing with time, then this work done will be positive. Then work done is positive. If velocity is less than, final velocity is less than initial velocity, that means velocity is decreasing, then this difference will come in negative. So we say that work done is negative. Sometimes despite of movement, what we see that final velocity is equal to initial velocity. So in that case we can say that work done is zero. Work done is zero. Like if a particle is moving in a circle, okay, and with moving with constant speed, that we call as uniform circular motion. Speed is constant. Uniform circular motion. If uniform circular motion particle is moving, that means speed is constant. It means that kinetic energy is constant. Kinetic energy is constant. There is no change in kinetic energy. So we can say that here also work done will be zero. So this is another method to find the work done. Please copy Neil if you understand.
Yes, sir, done. Yes, sir.
Okay, understood, Neil, this concept about energy.
Yes, sir.
Neil?
Yes, sir.
Okay. Now, as we know that this is a kinetic energy, uh, I told you that kinetic energy is basically momentum p square by 2m. So it's like a quadratic equation. If you see, it's a quadratic equation. So the graph will be, if I want to find the kinetic energy, if I try to find the kinetic energy and momentum graph, it should be parabolic graph. Or it will be parabolic graph. Parabolic curve. Okay. Okay, Neil.
Yes.
Okay. Now let's discuss about potential energy. Potential energy is something like if your body is not moving, but body has the ability to do work. This I can say that the energy possessed by body, the energy possessed by a body due to energy produced by a body due to change in position, change in position, shape, or configuration, or configuration. The energy produced by a body due to change in position, shape, or configuration is called as potential energy. Now, Neil, you if you might have noticed that whenever you want to do whenever you want to change the position, or you want to change the shape, or you want to change the configuration, you have to do some kind of work, right?
Yes.
So whatever work you do to change the position of a object or change its shape or configuration, that work is stored inside the body as the potential energy. So we can say that the work done on a body to change its shape or position, whatever work you have done to change its shape or position, that work is basically stored in it, stored in body, stored in it as its potential energy. You understood how potential energy is generated?
Yes.
But here one main concept that you should know about potential energy, that potential energy is only defined. Potential energy is only defined for conservative forces. Now we discuss what is a conservative force. The force are of we can divide the force on the basis of their work done in two categories. One we call as conservative force, other we call as non-conservative force. Do you know the difference between these two, Neil?
Yes, sir. Yes.
Yeah, please tell what is conservative force.
No, sir. No, sir. I don't know.
Okay. So conservative force is, that type of force whose work done does not depend upon the path followed by the particle. If work done by a force is independent of the path followed by the particle. If the work done by a force is independent of the path followed by the particle, then force is said to be conservative. Force is said to be conservative. That means it should not depend upon what path body is moving. So what depends upon work done only depends upon initial point and final point. That is, work done only depends upon initial and final points. Initial point and final points. That is called conservative force. There are only three conservative forces. One is gravitational force. Gravitational force. Second is spring force. Second is spring force. And third is electrostatic force. Electrostatic force. These forces are called as conservative force. Non-conservative force, if the work done depends upon the path, the force will be non-conservative, just opposite of it. If work done by a force depends upon the path followed by the particle, then force is called as, then the force is called as non-conservative. Non-conservative. For example, we can say as friction. पानी पियो, तो पानी इसको दे दीजिए मम्मी. Friction. Please note it, Neil.
Yes, sir. I'm doing that. Yes, sir. Done.
Okay. So you can see only these three forces are conservative. Three forces are conservative. So you will get only only three types of potential energy: gravitational potential energy, spring potential energy, and electrostatic potential energy, because there are three forces only. One more thing you should write in this conservative force, that total work done, total work done by a conservative force, total work done by a conservative force in a cyclic path. Cyclic path from where you have started, you have returned there only. Okay, will be zero. Okay, will be zero. What I mean to say that, let's suppose one particle I have taken here and I have done some kind of work. Then that same particle I have brought back to its initial position. So in this process, what you see, there will be same work done. Why? Because work done does not depend upon the path. It depends upon the initial point P and final point Q. So if you are going by this path, then also initial and final point are same. If you are coming back this path, the points are same, only path is different. So both will have same work done, but this will your direction is opposite, so it will be negative work done. That means here I can say, if this work done is W2, I can say that W1 is equal but negative of W2. So if you bring this that side, so what you find, the sum of both work done is zero. That is very, very important concept. Please write this also.
Yes, sir. I wrote.
Okay. So, any kind of conservative force, like if you are dealing with uh, gravitational force, or if you are dealing with spring force or electrostatic force, if you see the path is closed. Closed means cyclic. It's not like in this, it can be like this also, like this also. Okay, if you see the path is closed like this or like this, then in that case we can say that the total work done is always zero. Understood?
Understood.
Uh, so potential energy, there are different type of potential energy, their formula and their derivation, that we'll discuss in the next class. Okay,
Okay, sir.
bye.
Bye, sir.